Hello and welcome to the people here. Welcome to our Heron Talk with Carlini and Itay Yona. I'm Shani Golkevich, and I'm here with Ezra Hausdorf. And on behalf of our Heron team, we're very excited to have you all here tonight. So a few words about Heron. We're just a new initiative, and we're trying to expand the AI cybersecurity field. By introducing top-level cybersecurity talent into the field and to its opportunities. We're an NGO, we're based in Tel Aviv, and we're funded by Open Philanthropy, and it's a part of an understanding that protecting frontier AI should be an international priority. So our plan for tonight is a very anticipated talk from Carlini from Google DeepMind about his latest research. And after the talk, we'll have an open floor. We'll have an open floor with some questions, and leading the discussion will be Itay Yona. He's the youngest member of the same team in DeepMind. And if you want to ask any questions, you are welcome to use the Q&A function at the bottom of the screen. At the end of the session, we'd love for you all to stay for a few minutes to hear about Heron and our future plans. And yeah, and as for Asher Brass, who was scheduled to speak, we're saving him for another time, so stay tuned. Okay, I think we're ready. And I'm very excited to introduce Dr. Carlini. I think that's the one time I'm gonna use it. He's a leading researcher specializing in adversarial machine learning, model extraction attacks, and privacy vulnerabilities in neural networks. His award-winning research was also featured in the New York Times and in Nature magazine. And when he's not exposing vulnerabilities in AI systems, apparently he enjoys building fascinating side projects, like a fully functional CPU inside Game of Life. I don't know. Nicholas, the stage is yours.
Yeah, thanks. Yeah. Okay, let me share my screen. You can see this okay now?
Yeah.
Okay. Great. Yeah, so this talk should be roughly 30-ish minutes. I may cut a little bit so we have more time for questions, and we can always come back to this talk if people want to ask specific questions about that. I should just go through the talk end to end, and then we'll hold questions for the end. Is that how you prefer to do it? Okay. Okay. Yeah, I'll do that then. Great. So yeah, I titled this talk Practical Adversarial Machine Learning for the reason that for maybe roughly, I don't know, the last 2 years or so, I've been trying to think about what it means to consider this field of adversarial machine learning applied to the systems that we actually have in front of us today. I've been working on adversarial machine learning for quite some time, and for a very long time when we were doing this work, we were like conjuring problems to work on because there was no actual systems in front of us that we actually wanted to study. But then the world changed in a way that we were not yet really ready for, which is that machine learning started to work. When I started in this field, basically machine learning was an interesting academic discipline that we wrote lots of papers on, but people couldn't actually apply it in practice because the models just weren't good enough. You could have very specialized, small, localized models that people would use, but you wouldn't have models that were generally capable of doing anything interesting at all because we all just understood they weren't good enough. But then, sometime in the last couple of years, machine learning really started to cross the threshold where it goes from something that doesn't work well enough and is more expensive to use to something that's actually something people are willing to make use of. And this is a problem for us in the adversarial machine learning community because we thought that we had lots of time to solve our academic problems so that in the future, people would eventually have to look back on the classic literature and understand, how the attacks applied in the future. But it turns out that we're living in the future now, and we actually have to try and see what attacks look like. Okay. So let me give you an example. For a very long time, the most widely studied problem in adversarial machine learning is that of adversarial examples. There are thousands of papers on this topic, and they all start basically like this. You have some image, this is recognized correctly, as, in this case, a tabby cat by an ImageNet classifier. And you can introduce this adversarial perturbation that generates this new image here that looks essentially indistinguishable to all of us as humans. But if you ask the same classifier that gets the original image correct what this new image looks like, then the classifier tells you that this is 99% classified as guacamole. And of course, this is a problem, but this is mostly an academic problem, right? Because this is not something that people actually would do in real practice. And what this means is that we have lots of papers showing that these vulnerabilities exist, but we had very few actual real applied attacks because there was no actual system anyone would actually want to go and exploit. And to be clear, what I mean by a real attack here is an adversary where the attack is like the easiest way to actually achieve the end goal. So there were papers, for example, that would say, well, this adversarial example thing could be a problem for self-driving cars, because it turns out that you can put like an adversarial sticker on a stop sign so that a vision system, when looking at the stop sign, will misclassify it as now, let's say, a 45-mile-an-hour speed sign. And this is true. You can do this, but is it actually the case that the easiest way to cause the harm that you want, in this case, an accident on the road, is putting a sticker on a stop sign, hoping that a self-driving car recognizes it incorrectly and then crashes? No. There are easier ways to cause this harm. You know, I could just remove the stop sign. I could throw rocks at cars, right? The adversary who wants to cause damage is not restricted to doing this type of adversarial machine learning attack. And so the real attacks didn't actually use this for a very long time. And basically the fundamental observation I'm trying to make here is like, this is the kind of thing that we were studying, but like no one in the world actually cares about this kind of specific problem we've been studying. And so what I'd like to do is to try and understand what it might look like if we take these attacks that we've been doing in the literature for nearly 10 years and apply them into real production systems. And so that's what I talk about for maybe the next 20, 30 minutes or so, is how we've been trying to do this. Other people have been doing this too, but I'm going to focus on the work that we've been doing here and why I think this is an interesting problem for people to think about. Okay, so let me get started with one of the most common use cases I'm sure everyone has seen for these machine learning models recently, which is language models. So as I'm sure you've seen, these models are designed to be safe in all kinds of ways. And in particular, it's like the very simplest safety property that they have is they're supposed to reject instructions that are harmful. You know, so you ask it like, you know, generate a step-by-step plan to destroy humanity. And it'll say like, I'm sorry, I can't help you with that. And to be clear, in no way is the model ever going to give me an answer that actually would do this, right? Like the models are not smart enough to answer this, but you can hope that if the model has any safety at all, it will of course refuse answers to the questions, how do I kill literally all humans? Like if you can't even refuse answers to that, you're gonna have a very hard time doing anything else, which is strictly easier to defend against. You know, we ideally want models to be robust to prompt injection, which is like kind of like a SQL injection kind of thing. We want the models to refuse answers to abusive things, like generate me, you know, hate mail. We want to make models not be able to generate abusive images. All of that should be easier than like literally I want all humans dead. And so we said, well, what can we get like models to answer like arbitrary questions? And it turns out the answer here, again, using these exact same techniques, is yes. So I can do the same thing, it's step-by-step plan to destroy humanity. This time I'll paste in a text adversarial example, and the model will give me a response. And again, the response here, not very good. Like you can't like in 2 paragraphs just describe how to do any of these things. The point is that the model is responding. You have broken the safety mechanism, and the model is willing to give you an answer. And you can do this for any system that has these language models. As a component of it, you can add these adversarial examples and force them into complying with whatever the adversary wants and not what they were initially designed to do. So this, I think, is one very nice example of one of the ways in which we take the attacks that we have been working on for a very long time in the past and apply them into a system that we actually make use of. Okay, I have slides on how this works, but what I'm going to do for now is skip the slides on how we generate these adversarial examples because I want to focus a little bit more on the motivation, and I can come back to this if people want to hear this in more detail, but I'm just going to skip for a little bit these slides, except to say that the attack that we have here is very general. So what we do is we have this attack that allows us to, at the time when we wrote this last year, we could apply it to OpenAI's models, to Anthropic's models, to Google's models, to Facebook's models. All of these models were vulnerable to the same kind of attack, and we could fairly easily make them do arbitrary bad things. Okay, so let me pause for a second and talk about this attack. So this attack was an attack on one piece of a machine learning system. And what I'd like to do for 1 second is just like introduce what I mean by the machine learning system. So this is the diagram lots of people always show. And what happens here is you have some data, let's say it's emails or something, on the left. You feed this into some training pipeline, and the output of the training algorithm is some machine learning model, some neural network. Maybe it's doing classification, maybe it's a language model, maybe whatever it is, it's some system that is a result of the training process. And then you have, at test time, you feed other documents into this model, and you get some outputs. The output might be generate new text. In this case, I'm imagining you have some kind of spam classifier where you have, is this content, like spam or not, and the model saying yes or no, but you can have any kind of system here. This is like the general framework for how I like to think about the setup of machine learning. And the reason why I'm showing you this is that now you can start to talk about what various attacks actually do. So these adversarial examples that I just talked about are a kind of evasion attack, where they try and modify the input in order to make the output become misclassified. But the field of adversarial machine learning is very, very broad. And there are lots of attacks that you could imagine. And so what I'd like to do is talk about a couple of the other attacks, which I think are a little more subtle and have very direct parallels to other areas of security that I think are also very interesting that people think about maybe a little bit less. So to start, let me talk about poisoning. So poisoning is an attack that says what happens if the adversary doesn't control the images or text or whatever you have at test time. What if the adversary can control a very small fraction of the training data set and then uses this control over the training data to try and make the model produce the wrong output in certain controlled situations? Now, this is an attack that's been around for a very long time. In 2012, people were writing these poisoning papers showing that if you change these left images of a 7 and a 9 into an adversarial fuzzy versions of these 7s and 9s, then you can make these models perform very, very poorly at classifying small little MNIST images. And at the time, this work was important, and people have begun to increasingly appreciate just how important it is. Recently, this paper actually got a Test of Time award, which means 10 years after the fact, looking back, this was decided to be the most important paper accepted at this machine learning conference, which I guess really shows you how important these kinds of attacks are, that the machine learning community is awarding a Test of Time award to an attack paper that does adversarial machine learning work. Okay. But for a very long time, people looked at this in the same way that I told you that these adversarial examples were not actually something that were applied, because no one wants to put stickers on stop signs. You don't want to turn cats into guacamole. Under what setting are you actually going to be able to control the training data for these models? Because when this paper was written, like these are images from MNIST. MNIST is a data set that was initially collected in the early 90s by the US government, and then refined into a machine learning data set in the late 90s. So the probability that an attacker at the time decided that they were going to be malicious and modify the data set so that someone 20 years in the future, when training a classifier on it, would produce the wrong outputs is essentially zero. So like your adversary is either that person who has 20 years of foresight into the future, or like person with time machine who can go back and change the past. And like neither of these are very real attacks, right? And so like for a very long time, I and many others did not work on poisoning because we all just trained models on entirely clean data, because if you ever put any noisy data into your models, things were bad. And so why would an adversary be able to put arbitrary data into your models? Fast forward to today. Today, what do we train machine learning models on? the entire internet. Here's an example of a data set that people use today. It's called Lion 5 billion. It's a data set of 5 billion images and corresponding pieces of text from the internet. This is the data set that is used to train all of the best vision models that you can have seen. So if you've seen these clip models that can classify arbitrary images, these captioning models that can caption arbitrary images, if you've seen the generative diffusion models that can generate highly realistic images, stable diffusion and things like it, they're trained either on exactly this data set or data sets very, very similar to it. Now, this means that you're training a data set on something that anyone in the world could, in principle, have contributed data to. But again, you have this problem where probably when this data set was collected, everything was fine. Because like no one probably had the foresight to imagine the potential for an attack that they could then do 5 years in the future because someone's going to go and train a model on all of my data. Okay, so let's ask a simple question though, which is how do you distribute a data set that is this big? Like this is 5 billion images, it's like 100 terabytes on disk. Very hard to distribute this kind of data. And so the answer is, it turns out like you don't distribute this data set as it is because it is just very, very challenging to do. Instead, what you do is you just give a collection of URLs and the corresponding text that corresponds to them. And you tell people, here's a tool called image to data set. You can go download these images yourself. And this is what is done today. You just distribute maybe a couple gigabytes of these references and people go and find them themselves. Now, I mentioned earlier that the data set was probably not malicious when it was constructed because no one knew the images were going to be included in this data set, and so they were not being malicious ahead of time. But people download the data sets today. And so, who's to say that the data is not still malicious now? In particular, we make sort of in this one paper, a very, very trivial observation. Domain names expire. And what this means is that there are lots of domains in this data set that have since expired. When domain names expire, anyone can buy them again. In particular, I can buy them. So I now own 0.01% of Lion. So anyone who has gone and trained any of these models in the last year and a half or so has come to my server and said, please give me this image. I not only for the 5 billion, I also do for a bunch of other data sets that are partially either derived on Lion or have the same kind of property, but that they're just lists of URLs that you could just buy expired domains from. And so, if anyone has trained a model on any of these data sets in the last year or so, you've explicitly actually trusted me actually not to run the poisoning attack in practice. My server has some line of code, does Nicholas feel evil today? In the normal world, I respond 404 because, I like my job at Google. I don't want them to get mad at me. But at any point, if I wanted to, in principle, I could change this to be true. And then I can make the model return arbitrary poisoned images to anyone who would come for them. Now, this, I think, should change the way that we think about poisoning attacks. Because previously, we were living in a world where no one was using these models, and so it's not worth poisoning. And we were training on curated data sets that no one could possibly poison. Now we're living in a world where everyone is using these models, and the data is explicitly coming from places that an adversary could very, very easily control the data from. And to be clear, the attack here is not an interesting machine learning, clever, we did fancy math stuff. I may talk about that a little bit later if we have time. The attack is a very standard classical computer security thing that knows that sort of uses some understanding about how machine learning models are trained to then go and do something that causes damage without actually doing anything fancy in the machine learning world. Let me give you maybe one more example of an attack that we have on Wikipedia that works very similarly. So Wikipedia, I'm sure everyone knows, data set of, not data set, but it's used often as a data set as part of these machine learning models because of how high quality the data is. Wikipedia, though, has a vandalism problem. And people try and, for fun or for other reasons, just edit Wikipedia articles to say, funny things here in this example, like get a life loser in the middle of this biography, right? Okay, very funny, teenage humor, whatever. Now, the reason this is not a concern for machine learning models is because vandalism is well understood in Wikipedia and is reverted very quickly. So I could vandalize a Wikipedia page, and a minute or two later, someone will fix it back. And so in the normal world, everyone trains on Wikipedia because they have a very high degree of trust that the data set is very, very high quality. So it's seen in many ways as like the highest quality data on the internet you can find. Many machine learning models have explicitly stated that they train on Wikipedia explicitly even more than other data because of how high quality they trust it. So again, let's talk about what is actually going on when people train on Wikipedia. What did they do? What you don't do is you don't use a web crawler. You don't go and download each of the pages of Wikipedia one by one, because this is hard for Wikipedia to handle. You don't want to have just a millions of requests downloading your data set. Instead, Wikipedia provides, as a service, a database dump that you can just download it all at once. So they just you can download a couple hundred gigabytes of data that is like all of Wikipedia all at once. It's much cheaper for them to handle. This is a very nice service they provide. So this is what everyone uses when they train models on Wikipedia, one of these database dumps. The problem with database snapshots is they turn temporary vandalism into a part of the permanent record if you can time your vandalism right before the snapshot happens, but before the reversion happens. So if I can vandalize, then snapshot, and then reversion, it doesn't matter the revert happened on the live Wikipedia page. The snapshot has my poisoned data, and anyone who downloads a snapshot for the next however long the snapshot is valid for will get my poisoned data. So again, can I do this? Is this a thing that's a real attack? And it turns out the answer here again is yes. And the answer why is that they actually literally tell you down to the second when the snapshotting starts. They're a very open organization. So you can just scroll down on the page and it tells you, at this one's February 22nd, 3 seconds after after the half hour is when the dump is being started. Exactly when the snapshot starts. You can just exactly predict when you should be poisoning these pages. And then you can put arbitrary content on Wikipedia, which is of course, the most trusted source of truth that anyone has. Other websites poisoning in this way is strictly easier for many of these ways because there's even less quality control over the datasets. Okay, that's poisoning. I'll end then with one final attack, which is actually one I worked on with Itay a little bit, which is about something called model stealing. So this is an attack which is much more mathematical, but again, takes a look at the problem of machine learning from a different perspective than we usually think about it. So let me stop for a second and say what model stealing is. Model stealing is an attack that says, let's suppose an adversary is allowed to make queries to a model. So they control the inputs and they can make queries to a model, and they want to then figure out what the model is and if I can steal a copy of the model without having trained it myself. So we all know that model training is very, very expensive. I want to know, can I steal a copy of the model without having to have spent all of that money so that I have a copy of the model on my own disk? Now, in the past, we've written papers that are very academic. And we have shown, for example, how to steal models with, that are 2 layers deep with 400 neurons, or 1 layer deep with 1,000 parameters. It's these are very, very, very small things. Modern models have something, let's say tens, hundreds of billions of parameters. This is not something that's actually going to work in real practice. Not only that, we have a bunch of other assumptions that we make about these attacks, none of which are true in practice. We have just all kinds of assumptions that go into this. And that's why we have this paper as a crypto paper. It's a very, very theoretical result of what could be in some theoretical setting, but it doesn't actually apply to any real models that people actually use in practice. Now, we then start thinking about the question, can we make this real? Can we make this something that people actually want to work on as an actual problem? And in general, I was hopeful. The reason why I wanted to be this something that I wanted to submit to crypto is I thought this sounds like a problem for cryptographers. So let's write this up as a problem that they might be trying to think about, and let's see if they can go and take this and just figure everything out fairly trivially. And so this is my initial was my hope. It's like, maybe the problem is hard, but I just need smart cryptographers to think about it for a little while. They'll just give me the answer. So smart cryptographers did think about this for a little while. Here's a paper by, among others, Adi Shamir, where they make some significant improvements, but they don't just completely solve the problem. So it's good that they got something down to a more polynomial time, very important to have, but in no way does this immediately solve the problem. And that's what I was kind of hoping for. And this was, we wrote this first paper, Crypto, in 2020. So it's been, 4.5 years since then. So we've not really made significant progress on solving this problem completely. And so what I'm going to do is talk about one particular paper we had recently from this year that takes a different approach, which is just to dramatically reduce the expectations of what we want to achieve. The problem is in general quite hard. Let's just think of a much simpler problem. Okay, and so this is a paper that we titled Stealing Part of a Production Language. So this is what a modern language model looks like. There are lots of components to it that do many, many fancy different things. What we're going to do is we're going to steal one very small piece of the model. Okay, why this piece? Because it's the one I know how to steal. Okay, we can talk later about what actually value it provides, but it's a thing that we can actually do in practice, and that's what I want to talk about. It's how we can take attacks and think less about how do we steal the entire model impractically, about how we can steal small parts of models practically. Okay, I'm going to skip over some of the math here because I don't want to spend too much time in the details of this. But the basic idea of the attack is that we think of a machine learning model not as some machine learning system that these machine learning people care about. We think about it as just as a mathematical object. In principle, you have this ugly function that does various complicated things, and then you have a linear layer for the model. And what this means in practice, as an equation, is that your model, your neural network f of x, is just some linear matrix A times some complicated thing h. And what we're going to try and do is we're going to try and learn the value of A. And to be clear, most of the language model is not this last layer. Most of the model is this complicated function. I'm going to learn nothing about that. What I'm going to try and do is learn something about this matrix A. Now, I'm going to assume some amount of linear algebra knowledge for maybe 1.5 minutes or 2 minutes. If this is not you, sorry, feel free. I'll tell you when you can come back. Because I want to spend a minute or two just talking about the math, and then I'll let you know when it's safe to return. Okay, so the input dimension here, this means for these language models are tokens. They're one-dimensional objects. And the way these models work is internally, they have this representation space, which is something like 8,000 dimensions. And then this final layer is what turns the internal representations into the output words that we see. Most models know something like, let's say 100,000 different tokens. And so it goes up from 8,000 to 100,000 dimensions. And so what we are able to show is that because this is a matrix that that makes the input go to be a larger thing, if you query the model many different times, and I'm going to skip over this relatively quickly, then what you end up with is a matrix that in some sense is overdetermined and allows you, if you do some fancy math by just applying the singular value decomposition, to do something, I'm going to skip this here, to recover the weights of the model. And I know that I've skipped the entire part of how we actually do this. It turns out that if you just query the model and do the singular value decomposition, that actually just gives you the last layer. You have to believe me or read the paper afterwards, because I want to make sure I have lots of time for questions. I can come back to this if people want. But what we actually do is we can actually use this and apply it to real production models people actually use. So we did this for a couple models that OpenAI served. We got their permission ahead of time. We made sure that we did this very, very carefully. We destroyed the data afterwards. But what we can do is we can learn not only the final layer, but also roughly how big the model is, which by itself is interesting because this is something that people don't actually publish. And so we were able to confirm in this paper for the first time that some of OpenAI's models called Ada and Babbage were, internally 1024 and 2048 dimension. We also, as part of this, learned the size of GPT 3.5 Turbo, which is, again, something that actually no one else in the world knows, except current and former employees at OpenAI that now we know. So like again, like if you wanted to actually learn this, like suppose you want to be an actual attacker to do this, like there are two ways you could learn this information. One is you could try and like actually like do standard security attacks and steal it from OpenAI servers, like break into OpenAI. The others you can do is machine learning attack and have this work. So again, like I think this is like a very real in this kind of attack setting because this like actually is the easiest way to get this data. Unfortunately, I can't tell you this number because we agreed with OpenAI that like we would run the attack. We wouldn't actually disclose the result of it. I think this makes sense for everyone. Okay. Very good. So yeah, I have about 25 minutes for questions. So the basic conclusion I want to leave with, I'm going to skip this one too because this is a little less interesting, is to say that we have tried to do as many attacks as we practically could on many different aspects of the machine learning pipeline in order to show the way that these attacks tend to work and that we can make them be applied to real production systems that people use and not just these academic things that we've been playing with in the past. So for a very long time, when I gave talks, I had a slide that said something like this. The adversarial machine learning is the art of making up adversaries so you can write papers about problems that don't exist. And the reason why I said this is because there were no real things to attack. So like, what do you do when there's nothing real to attack? You don't want to just not do security. Like you have to do something. So what people would do is they'd write a paper where they say, imagine in the future, we were living in a world where setting. Then they would write the paper that said how the bad thing could happen. And what I think is interesting about this is that this worked. Because in the span of maybe 1 or 2 years, we were very quickly able to take all of these very theoretical attacks that we had and apply them to real production systems that we have in front of us now. And what this means is I'm not going to say that it's bad that we did this. I think we should still be doing this even today. Today, we should be hypothesizing what if people use machine learning models, these language models, in some other setting that they're not currently doing, so that in the future, when we actually do go and use them in something like that, we have ready available to us the tools to do these attacks. But the pitch I want to make for this talk is that we now have a lot of tools and an increasing number of applications where these models are being deployed. And I would like us to think quite hard about how to take those attacks and make them work on the real systems we have in front of us so that we can know what is the space of the vulnerabilities that exist. Because I would ideally like to be in a world where we know everything that is possible from an attack side so that we can then go and defend against it. What I would be really worried about is to have attacks that we don't know are possible and people then go and build systems, assuming that models are going to be robust to a certain class of attack. And only after they're widely deployed do we then go and figure out how to actually exploit them. That would be pretty bad. What I'd much rather have happen is for us to know all of the attacks that are possible so that people can then consciously make a decision, should I deploy this system or not, in light of the vulnerabilities that are surrounding the system. So that's all I have. I'm happy to take questions for the next 20 minutes or so. And if you have any other questions you want to email me afterwards, here's ways to contact me. Thank you very much. And let's go to some of the questions.
Well, this was amazing and funny, unexpectedly. Okay, so we're opening the floor for questions, and I'm gonna invite Itay Yona to facilitate the discussion. So Itay has an InfoSec background from the IDF. He developed an AGI obsession, and that's guided his career from neuroscience to DeepMind. And a few years ago, he initiated a reading and hackathon group for mechanistic interruptibility, bringing together over 300 scholars from cybersecurity, neuroscience, and AI. And actually, their work was recognized with a grant from the Long-Term Future Fund in 2023. So Itay, the floor is yours.
Hi, everyone. Thanks, Nicholas, for the amazing talk. I will say that before I joined the team, I was advised by my manager, like the CISO of DeepMind, to read a bit about what other researchers are doing. And my plan was like to join as to do a bit of like security engineering, and then obviously move to like a Nobel Prize winning scientific effort. But then I came across like Nicholas' blog, and he has basically a similar talk. And I thought, oh, okay, this is like super, like way cooler than what I thought. So maybe like I can actually join the team and work on the things that we do. So before I start with the questions, I will share a disclosure that, as Shani said, like both me and Nicholas are in the same team. We have different perspectives, obviously. Like Nicholas is the most senior researcher, and I am the last one to join. But I think, given my trajectory from the information security community in Israel to machine learning security in DeepMind, I'm basically in a very unique position to bridge Nicola's expertise with the audience's background. In the set of questions I assembled, I will mostly focus on high-level overview of machine learning security and how people can have high impactful career or projects in the field. And we will have time for questions from the audience, so feel free to write them in the chat. So the first question is as follows. So given your background in your focus on breaking AI systems, do you believe it's possible to create truly secure AI, or are there any fundamental flaws that can be addressed?
Yeah, so saying truly secure AI is kind of like saying, a truly secure software system. Now, this does not exist. What does exist is systems that are secure enough for the way that we want to use them. And so this, I think, in principle, should be able to be done, right? Like we figured this out in software security. We figured it out in cryptography. We figured it out in most other areas, how to design a system which is sufficiently safe for the way in which we want to make use of it. And so maybe what this means is if you want to use a machine learning model today to do something very, very, very sensitive, the answer is just don't use it. Now you're secure against all of these kinds of machine learning fancy attacks. But maybe what you're doing is you're building an application for kids that has no safety sort of things that it needs at all. You're like relatively confident that like the worst harm that's going to happen is like, you misclassify like a type of a flower, and like, maybe now like it's not great, but like there's no actual damage to anyone, and you're like, fine, good enough, I'll launch the thing. But you decide I'm not going to maybe use this in a setting where I actually need to be guaranteed that every answer is correct. I think that is probably what we're going to have to do for at least the next couple of years. I don't think we're going to have any really strong defenses as strong as we have in software security or cryptography for at least the next couple of years. We've been trying for a very long time. It's a very hard problem to solve. But I think we can try very hard to build systems around the machine learning models that make the systems as a whole much more secure, even if the model itself is brittle. I think there's a lot of interesting work being done here. And I think, like we should never be afraid that we can't make everything perfect to not try and make things better.
Cool. Okay, so basically, if we have an attackers defenders trade-off, you're saying that in the current state of affairs, and even in the foreseeable future, there is going to be a huge advantage to attackers.
Yeah, just because empirically this is what has been true for the last several years, where people have been working on defenses for adversarial examples and other things for a very long time, and have made progress, but the progress that has been made has been much less significant than the progress that's been made on attacks. Like we are better at attacks than we are at defenses currently, and the progress on attacks is outpacing the progress on defenses, I think. But at some point, I think this is likely to change. I just don't know what that point is. I think it's just not right now.
Cool. Okay. So the second question is, do you think working in a leading AI lab like DeepMind, OpenAI, Anthropic, or others is dramatically more impactful than other avenues of ML security research, like academia or like smaller startups or organizations?
No. Most research that is done is not done at big labs. And so most of the impact, I feel like, on many of these things is by people who are doing their PhDs, people who are faculty at these universities doing very important work. The difference, maybe let me step back. Okay, so why am I here if I don't think that it's like you have to be here to do this stuff? I like doing the technical work myself. It's like I like getting my hands on actually writing the code to solve the problems. And because of the way that academia works, if you want to be a faculty, you very quickly become a manager. And I did not want to become a manager. I wanted to do technical work. And so the best place, like the reason why I'm at DeepMind is not necessarily for the resources, although that is nice to have lots of compute, is because I want to be somewhere that lets me do the technical work. So that's the sort of the answer to that piece. But I do think that doing a lot of these things, let's see. So of the papers that I just talked about today, for example, none of them required significant compute access to these kinds of things. You know, the first paper was mostly led by some researchers at CMU, Zico Coulter and some of his students, right? This did not need to be at DeepMind. The one on poisoning, like it cost us $60 to buy some domains or something like that. Maybe $100 something to buy some domain names. Like there's no vast resources of compute, no fancy machine learning stuff there. The model stealing one, you know, again, like it was the very cheapest stealing attack. It cost us, you know, $100 or something. You know, like there definitely are papers that you could only do in big labs. I think the nice thing about applied security stuff is that it's not the case you have to be there in order to do these kinds of things.
Cool. But apart from the resources point of view, maybe like being in DeepMind gives you a much more information about the know-hows, like the technical.
Oh, sure, yeah. Okay, yeah. So I mean, like, you know, this is true anywhere.
Yeah, but I just wanted to say also the ability to predict how AI will look like in the future is probably much easier to do from an insider.
Sure. Yeah, this is definitely true. You do get to see where things are going before things land. However, it's not obvious to me how much more this gets you. Like maybe it gets you another 3 months or something, but like no one predicted what ChatGPT would become, even the people who built it. And so for many of these things, you get to talk to people who are excited about this, which I think you could get anywhere. And you can see a little bit behind the scenes of where the products are going. But in any research area, it's very hard to predict maybe a year out what this is actually going to be looking like, because the impact is driven not only by what you're building, but by like how well it actually works, which is very hard to predict in the first case. And so I think, yeah, there definitely is some amount of value of things that you learn like this, but I don't think there are not many questions where I feel like this would be a limiting factor in whether or not you could answer these things. I feel like you could do a very high quality job at doing these kinds of things, not at these places. Like nothing that I again presented here was specialized fancy knowledge that needed like to know where these things were heading.
Mm-hmm. Okay, interesting. The third question would be, okay, so sometimes security vulnerabilities, they are erased from misaligned assumptions. So do you think there are big differences between your perspective and the classical machine learning practitioner?
Yeah, this is a very good framing of the question. Yeah, what is an attack? Like when you want to exploit something, almost always what you're doing is you are using the fact that you understand something about the world better than the person who built it. Like you understand that there's something that you can do that an attacker can control some piece of data that they didn't quite understand was controlled by an adversary. I don't think there's anything in particular that I do differently here. I think it's mainly just the fact that you have to, whenever you see a new thing, people who are normal people ask, like, what can I do with it? And the security people ask, how can I break it? And you just like, this is the question you have to ask. Anytime you see a new thing, you run through the list of attacks. Does this help me do adversarial examples easier? Can I attack this as adversarial examples? Can I use this to make poisoning easier? Can I poison this? Can I use this to do data extraction? Can I do data extraction on this? Like you sort of run through the list and you try and figure out like what does this new thing mean? What are the attacks are possible now as a result of this? How can I exploit this? And every time a new thing comes out, you spend a bunch of time thinking about this. And eventually you'll sort of find one or two areas where people hadn't quite thought of attacks that are possible because of the way that we handle various things. So I think, yeah, it is very much a frame of mind. I don't think it's my frame of mind. I think it's just like the security researcher's frame of mind, which is maybe different from the machine learning researcher's frame of mind.
Cool. Thanks a lot. I will now I'll pick some questions from the audience. Okay. So Raz, maybe I should keep it anonymous. So someone is asking, thank you for the amazing and interesting talk. What kind of a threat model do you assume on the last model stealing paper? So what kind of threat model?
Yeah, standard query access to the API as provided by OpenAI.
Okay.
At the time that we did the attack. They have since changed the API to prevent the attack, which is good. This thing is one of the nice things. Like, how do you know that you have succeeded as a security researcher? You've succeeded when you have shown an attack so compelling that people are willing to make breaking changes to the API to prevent your attack. Like, this is sort of the definition, I think, of success for these kinds of attacks. You have people introduce Spectre and Meltdown, and then you like change the hardware to make the attacks harder. Here we have an attack that worked because of some APIs that they allowed in both log probs and something called logit bias. And as a result of this, they've removed the ability to do some interactions between these that made the attack not work anymore, which made the models a little bit less useful, not very much, but a tiny bit, but made the security quite a bit better in this way.
Cool. Okay, another question. Do you know of any monitoring of the major training data sources? For example, hashes of the images you talked about, or automatic detection of poison text before training starts?
Yeah, so now the big data sets do have hashes because we showed the attack, so it's great to see. Some of them, the default is that the hashes are disabled. And unfortunately, this is for a very good reason, which is that a large fraction of the images online change fairly regularly because people re-encode them with a new codec, or because they are like, stock photos and they change the watermark on the stock photo, or for lots of reasons. And what this means is that if you're using a cryptographic hash, then a lot of the images will have invalid hashes after even a period of like 1 to 2 years. As an example, something like a third of the images in, I think it's a 3-year period, have the hashes become different, but the image is essentially still the same. So it's a lot of data you use if you check the hashes on these things. And so people, for very good reasons, sometimes decide utility over security here. I want more images, I'm going to turn the hashes off. You could also, for example, try and look for poisoning. And there's a lot of work looking at this that tries to try and find it. This is a needle in a haystack problem because you have hundreds of terabytes of data and you have to find a couple poisoned images. And there are techniques that are relatively effective at doing this. But again, this adds additional cost. And the question is, are the people willing to pay that cost? I don't really know for the biggest models that are being trained today whether or not people want to do that, but there's a lot of work being done here to try and identify these kinds of poisoned images. And I think this is like the best that we can hope for the attacks, is we can say, here is a thing that is possible. It is now up to you to decide how bad it is and what kind of cost you want to pay in order to try and prevent it. And as long as the defenders are making an informed decision, I am somewhat agnostic to what decision it is that they make, as long as they're making the decision and being aware that they are introducing some vulnerability as a result of making some kind of trade-off.
Cool. I will rephrase the next question, which is about like which systems are mostly under danger? Is it like fine-tuned models, RAG systems, or like a plug-and-play GPT and some system prompt which are vulnerable?
I don't know. I feel like there are a lot. I think it's hard to answer the question most vulnerable, because like they're all pretty vulnerable. And so it's hard to know which one of the ones I think is most vulnerable. I think it really depends on how you're using the model. Like, what does the adversary actually want? And as a result of what they want, which system becomes more or less vulnerable. You know, if you're doing RAG over legal documents produced by the courts, presumably this is all clean data and they're not being malicious. If you're doing RAG over emails that I receive, now RAG seems very, very vulnerable because anyone can send me an email with malicious content. You know, so I don't know, like it's very hard to answer on in the broad way. I feel like it really depends on the specifics of how the system's being used.
Cool. Next is about the difference between computer vision and LLMs. So it states that in computer vision we have a well-defined threat model, but how do you view this from the context of language models?
Yeah, so this is true. In computer vision, we tended to consider adversarial examples where we looked at, you know, small pixel perturbations to images so that the person would say they look the same, but the model would classify it differently. In language models, we don't have these same kinds of definitions. In some sense, I'm okay with this because the toy game we set ourselves out for in computer vision was never the problem we cared about in the first place. Like, it's very rarely the case that making small perturbations to images that the human will label consistently is actually the problem you want to solve. What you want is a robust classifier to attack. We just set ourselves a very small problem that's like necessary but not sufficient. I think we don't have in quite the same way the necessary but not sufficient setting for language models. But in some sense, I might feel maybe okay with that because in computer vision, I think we may be overly obsessed over this very, very small problem and did too much work on that and let a bunch of other work stagnate on other areas that were a little bit more broad. And my hope is that maybe in language models, if we don't have this very, very, very narrow problem that turns out to be very hard, we might think about other kinds of settings instead of just trying to solve and failing at solving one very, very specific problem.
Cool. Just before I move on, just let me verify. Do we have a couple more minutes after 6, which is for me? Because
I have more time after.
Many questions. Okay, so the next one would be okay, about the fact that adversarial examples are usually focused on a very local manipulation. Do we have some efforts where we find or look for global adversarial examples? Do we have like symbolic techniques for finding adversarial examples?
Yeah, so we do. So a long time ago, 2018, there's a paper that I helped a little bit on that was called Unrestricted Adversarial Examples that tried to pose the problem that we actually care about, which is it possible to make a classifier produce the wrong output without any bounds on the particular constraints to the perturbation? So I was just like, I want the model to make a mistake, a confident mistake, but a mistake. I think this was a very, very nice paper. It turned out, though, that the sub-problem of the images that look the same but still are classified differently was so hard that we didn't really get a lot of people trying to do the unrestricted attacks because the other attacks are still possible and easy. And so it's not really worth trying to defend against the entire big giant problem if you can't even solve the small little problem. And my hope is that maybe text is different, that, you know, there might be reasons why some attacks are harder, and that people might be more willing to look at these global attacks, especially because in many cases we don't have the same assumptions that go into these image classifier attacks. So I do think there's a bunch of work to be looking at here. But we did try and do this for vision. We just didn't work that much on it because the attacks happened to be so easy.
Cool. I will go back to my questions. So, okay, so mine was like about the fact that machine learning security is a multidisciplinary field. We have both. So the question is how these two fields interact, and I think you already alluded to that in saying that you have an adversarial mindset. But can you explain how these two fields, which role each field play?
Yeah. So security is an interesting field because you can have security plus arbitrary other field in computer science. And usually what it means, you know, is just the fact that when you're working in the other area, you're thinking about everything that they can do and how an attacker can enter into that. And just like you can imagine security in IoT devices or security and networking and all of these things, it's the exact same thing for security and machine learning. You have to have some background on machine learning, some background on security, and then you just look at it, what's going on, and you say, how does an adversary interact here? I think it's entirely consistent in spirit with how security interacts with all these other fields.
Cool. So does that mean, let's say someone is a security expert that has been working on vulnerability research or reverse engineering, does it mean that it should be easy for him to switch to machine learning security, or how do you see it?
Yeah, okay, so I did this. It was earlier in the machine learning time, so there were fewer things. But yeah, I started my PhD in software security. So I did return-oriented programming, did a bunch of very low-level software security exploits. I was at Intel for a summer, working on some on-chip defenses to prevent some exploits. And yeah, so I was very, very in the weeds software security. And then I decided I wanted to do some. I couldn't figure out what to do for my dissertation. Like most problems in software security are they're not solved, but we have a very good understanding of what's going on, and I wanted something that seemed more like the Wild West, and that looked like machine learning in 2018 or 2016, something around 2016, something like that. And so I switched to machine learning around then, and there was a lot less going on, so it was a lot easier at the time. But I definitely think it's possible to make the switch. I think it takes some amount of time to get used to the new field and to understand what's going on, but I think it's entirely doable. I think there are more now, but there are still not as many people who enter through security and then go into machine learning. And I think this is part of the reason why I've had some success in some of these papers that we've written is, this poisoning paper I talked about earlier. This is not a machine learning paper. This is a paper that is about an application of machine learning, training on training data sets, but it's a very security kind of paper of how do I modify the data that's going into this thing? What are the assumptions? It's trivial, but like a machine learning person would not write this paper. You need a security person to write this paper. I think there are lots of things like this where you need to have a very good understanding of exactly what is happening in the machine learning space. But then you can go and do your security kinds of research in order to make these kinds of things to show what the vulnerabilities are.
Cool. And maybe my last question would be, so you said you started since 2016. So has there been anything that has been particularly surprising for you, like some finding or paper which you are not on it, that you just were that's change your expectations or your perspectives?
I mean, the field has changed quite significantly since then. So I guess the answer is yes. There are huge numbers of things that have changed very significantly in the last several years. They're very hard to list many of them. Do you mean papers though, specifically in adversarial machine learning or machine learning generally, or what?
No, I meant I refer to machine learning security, but actually you can answer about, I think, machine learning in general if there is some, I don't know.
Yeah, okay. Machine learning security. Let's see. There are a lot of papers that I think are very, very compelling. I think most recently, some of the things I'm most interested in seeing other people working on are a bunch of the papers in the direction of showing that you can take models that are trained with safety classifier, or they're trained to be safe, and you can do a very, very, very small amount of fine tuning and the safety goes away. I think this is a fascinating result that safety appears to be such a surface level thing that is being done. I think there's a lot of work that's interesting happening trying to show how to make this not be the case. Yeah, there's just whole directions of attacks that on language models in particular and other things that I have done very, very little on that I think are just very, very nice. The field of machine learning has grown so significantly. Yeah, so in 2016, I feel like I could read every paper on adversarial machine learning. And then, maybe a couple of years later, I could read every abstract. I couldn't read all the papers, but like I sort of knew which ones were interesting. And then, a year or two later, I could like see the titles. And like now I feel like there are papers where I see the titles that are interesting that I hadn't seen, in like a year. And like it's even harder to keep track. But yeah, there's a lot of really nice stuff that basically takes inspiration by what people are doing and then tries to come up with the most clever attacks on these things. And so yeah, I'm excited by a lot of these things.
Cool. Thanks a lot.
I have a question.
Yes.
I'm using my my prerogative. It's actually for both of you. It's regarding your background in adversarial and the way you started, and actually where Itay is located and where he's coming from in his background. I wonder how your path is different and how it feels different from the way you described Nicholas in the beginning and what Itay is experiencing right now, from his different perspective.
So is it a question for me, I guess? So maybe I'll say I couldn't agree more with Nicholas when he said that you can apply security to any computer science domain. And actually, I was lucky to start with applying security to mathematical problems and then security to hardware, like electrical engineering sort of domains. And then I sort of formed my identity as like an interdisciplinary researcher. This is what I thought, or what I still think I am. And that led me to this neuroscience AI sort of kind of aspiration, like to study both of them as an interdisciplinary field. And so I think I'm very much aligned with that. So now realizing that machine learning became extremely practical and breaking it might be like much more exciting than like small toy examples. I thought it would be cool to once again apply security to this new just like extremely fast-pacing domain of machine learning. So it's like an opportunity to being at the frontier of things that are constantly changing, and then I could bring this perspective. So on that end, I think I'm very much aligned. My path, my trajectory went through neuroscience and also a lot of reverse engineering. I did a lot of like even hardware reverse engineering. And it gave me this strong conviction that you can take any sort of computation and understand it. So like compress it into a small set of meaningful descriptions. And it's something that I still sort of have in my mind, like it's a strong bias. I still think you can take a neural network, biological, but mainly like artificial one, and like reverse engineer it and make and come up with a description of what kind of computation is going on. And you can use that to both break the system, but also maybe to steer it, control it, and make it safer. And I think it's something that it's like one of my personal biases, given my trajectory. It's something that Nicholas not necessarily possess.
Yeah, good. That was a very different answer than I was expecting. But that's why you ask questions, I guess. Nicholas, there are a few more questions from the audience, if that's okay.
Sure.
Sure. Itay, do you want to do it?
Yeah, I will be able to paraphrase them if necessary. So so it's like it's about why the research community targets L norms of like small perturbations. Is it because it's easy to specify, or is it because the only practical machine learning systems were around spam filters?
Yeah. Okay. Because it is a problem that seemed like it should be trivial, if you can exploit this, then you could probably do literally anything else, and we couldn't solve it. Like this, I think, is the motivation that I would give as a defense to these kinds of small norm attacks. Like, if I can make two images be classified differently that look identical, then I almost certainly could just generate a new image that is classified incorrect. Like that's a strictly easier problem. And so it is a very restricted kind of thing to attack. I think defending against this does not imply robustness to the whole field, to everything, but at least for fixing it, it's clear that we would need to at least fix this. And so if you don't have defenses here, then you're not going to have defenses that fix everything. And so I think, we initially set this out as a small problem that we thought would be relatively straightforward to fix. It turned out that it was very, very hard. But this means that, we just need to do more work on it and figure things out. I think there are also good reasons to ignore this problem and try and focus on the broader problem as a whole. I think, we probably went too far in the direction of just looking at these small LP attacks. But I will still defend that it is a problem that we do need to be able to figure out at some point. It just maybe the fraction of work that went into the field was maybe too high on this particular sub area of things. For example, the assumptions that go into here are often the case that the adversary has full white box access to the system. In many, especially today, production settings, no one else has access to the weights of these models. And so thinking a lot more about these black box attacks makes a lot of sense to me. You'll still need to solve the small perturbation problem, but maybe in the black box setting, this is a more interesting problem to think about today. I think there are lots of ways of adjusting the problem to the threat models that we have available to us today that could make this more interesting. But yeah, I still think the problem, at least in itself, is still interesting.
Cool. And then last question from the audience is about how can the research community bridge the knowledge gap between its side and the policymakers?
This is a very good question for someone who knows anything about policy, which I do not. I feel like there are some people in the world who are good at this kind of thing, and just like I come from standard security and then go into machine learning. I feel like we need lots of people who are policy people who want to learn about this adversarial machine learning thing. It would be great if we had more machine learning people who wanted to think about policy. This I think is very important, but I don't feel particularly qualified to give any meaningful answer here.
Yeah, maybe I can address this because in ICML last year there was a small workshop about policy making, and there was some people from our team managed to summarize a lot of the issues and problems of unlearning in a way that was meant to be communicated to policymakers. So I think you could be like a top researcher and use your knowledge in order to be able to distill and crystallize a lot of like small papers and small improvements in a way that could be meaningful for policymakers. And then they just made it very clear that this problem is extremely hard, which is it's a very good sort of a point you could communicate. And I think that's one way, at least, that I found inspiring. And
that's good advice. Yeah.
Okay. That was my part, and thanks everybody.
So thank you very much, Nicholas and Itay, and for everyone who stayed with us this whole time. This was a very fun conversation and a very technically challenging experiment. Yeah, thanks a lot. Have a good night.
Yeah, thank you.
Bye-bye.
Bye.